And I'm just going to grab a new one. All right. And okay, so the second question asks, what is the acceleration due to gravity on the moon's surface? So our gravitational equation is just gm1 m2 over r12. So in this case, well, for all cases, I guess, the gravitational equation, the gravitational constant g is 6.674 times 10 to the minus 11 newtons, and that should be squared, sorry, meters squared per kilogram squared. Now in this example, we're going to use m1 as the mass of the moon, which would be 7.346 times 10 to the 22 kilograms, and R12 would then be the distance from the center to the surface of the moon, or the radius of the moon. So the radius of the moon is just 1.738 times 10 to the 6 meters. And we want the gravity on the moon's surface, so we actually don't need the m2. And to illustrate this, well, our force is just gm1 m2 over r12, and that force is going to be m2a, right? So F equals ma, where m2 is the mass of whatever the object is we're considering, and that's the gravitational force. So you see here that m2 cancels in both cases, or both sides of the equation. So then that means that a is our acceleration, which in this case is our gravitational acceleration. So a is just equal to gm1 over, and I keep dropping that squared, over r12 squared. Okay, now filling in our values. Our gravitational acceleration is 6.674 times 10 to the minus 11 newtons meters squared per kilogram squared. Mass of the moon and 1.738 times 10 to the 6 meters. Meters squared. Okay, so just doing a quick unit check here. So we've got meters, they'll be squared down here, so they're going to cancel this. This kilogram will cancel one of those. And then remember that a newton is a kilogram meter per second squared. So that means this kilogram will cancel the rest of the kilograms and leave us with meters per second squared, which is a unit for acceleration. So that's great. That means we've likely not made any mistakes because the units work out, and that is unlikely to happen if we made a mistake. Or at least is one of what I would recommend is one of the first checks you should make if you think that you made an error. Okay, so running this through our calculator, we get our acceleration is 1.623 meters per second squared. And so the gravitational acceleration on the planet of the moon, or the surface of the moon, is 1.623 meters per second squared. Checking the solution, so we just use this expression. So they're just starting from just an equation for it, but I often just opt to not remembering a bunch of equations, but just the primary equations. and then knowing how to get to each piece, but it's up to you. And so you fill in the numbers and you get your gravitational acceleration. So that looks good. And grab a new one. Okay. All right. And now this question, I'm going to just draw it out here. So we've got a positive charge, and a point. And it says that, now let's see if I can do this. Okay, it says that that's our, and the charge on this guy here is 3.0 nanocoulombs, and the charge on this guy here is 3.0 nanocoulombs. Okay, and so it asks what the magnitude and direction of the electric field at the position indicated, so that would be this guy, by the dot in the figure. So first off, we need electric field. So again, I'm just gonna, and also this is question 3. I'm just gonna go through this little square I've drawn before. And so force and electric field are related by charge. Potential energy is by a minus dx. Potential is charge, and potential and E field is by dx. I just mentioned it because I usually remember the force equation, which is the force from electric charges is 1 over 4 pi epsilon naught Q1 Q2 over R squared, R12. So the E field equation, and I should also say R12 R hat, just so that, because we're going to be dealing with more than one dimension, so it's going to be handy to keep our vector notation in hand. So going from force to electric field would be division by Q. So get rid of one of those Q's. So then E is 1 over 4 pi epsilon naught Q1 over R12 squared R12 hat. Okay, so that's our E field expression that we're going to use to solve this. The other thing we're going to need is to set up an axis system. So let's throw the origin right in the middle, and we're going to have X go this way, and so that'll be our X hat. And we're going to have Y go up right this way, Y hat. And so then now we need to define a couple of our R12 vectors. So going from this positive charge down to here, and I'm going to call that R1. And going from here up to here, and I'm going to call that R2. Okay, so R1 is, so looking at it from the positive charge, right? So that's minus R in the Y hat, minus X in the X hat. So minus R X hat, minus R Y hat. The magnitude of R1 is the square root of the sum of the squares, so R squared plus R squared, which is root 2R. And so R1 hat is R1 vector over, I'm just going to erase that and fix it, R1 vector over the magnitude of R1 vector. I'm just going to scroll this up. Which equals minus r over root 2 r x hat minus r over root 2 r y hat. So the r's will cancel, giving us minus 1 over root 2 x hat minus 1 over root 2 y hat. Okay, so there's all of our stuff for our one vector. And now looking, we can see from that our R2 vector, which goes from this charge to here, is plus r in the y hat and minus r in the x hat. Minus r in the x hat and plus r in the y hat. Oops. No, you bad thing. Stop that. What did you just do to me? Oh, alright, you go there. Sounds good. Okay, so R2 vector is, what did I say? Minus r in the x hat plus r in the y hat. Magnitude of R2 is just root r squared plus r squared, so just the x component squared plus the y component squared, which is root 2r. I'm just going to circle these to differentiate them, and also because I'm going to need them later. Okay, and so then the R2 hat vector is again minus r over root 2r x hat plus r over root 2r y hat. The r's are going to cancel, and so R2 hat is minus one over root 2 x hat plus 1 over root 2 y hat. Alright, so now it's going to be helpful to collect everything we need. So I'm just going to move up everything here. So we have that our electric field due to a charge is 1 over 4 pi epsilon naught times the charge over r12 squared times r12 hat. So this is the distance between the charge and the point, and the unit vector between the charge and the point. So we've got two charges, 2 points, so our total electric field will just be the sum, but we can break it up into the different pieces. So we're going to have an E1, and that's going to be 1 over 4 pi epsilon naught. The charge is 3 nanocoulombs. The r vector is just the magnitude, which, if we look, right, both of our magnitudes, our r1 is just root 2r. So it'll be root 2 r squared, and then multiplied by our r1 hat, which in this case is minus 1 over root 2 x hat minus 1 over root 2 y hat. Right, so that would be our r1 hat, which is this guy here. All right. So now just multiplying this through. I'm not going to bother doing the calculation for 4 pi epsilon naught since we're also not given the value of r. So I'm just going to leave things the way they are. And so this will be 3.0 nanocoulombs over, so root 2 squared is going to be 2, so this will be 8 pi epsilon naught r squared. So that's just this piece. And I'm going to keep the, or I might as well, I guess, pull the root 2 out just for simplicity here. So I'm just going to pull out the root 2. So throw the root 2 out front. And then this will just be minus 1 x hat minus 1 y hat, like that. And now we're going to play the same game with 2. So the electric field due to the second charge is 1 over 4 pi epsilon naught, 3.0 nanocoulombs, and that's because our second charge in the figure is also 3 nanocoulombs. And also, if we look, our R2 magnitude is root 2r, which is this guy here. And our unit vector is similar, but with a positive on the y. Okay? So this would be root 2r squared, and then minus 1 over root 2x hat, plus 1 over root 2y hat. So again, I'm not going to bother calculating everything because we don't have the value of r anyway, so I'm just going to leave it as is but pull everything out. So root 2 squared is 2 times 4 is 8, and I'm going to pull the root 2 out here. So this would be 3.0 nanocoulombs over root 2 8 pi epsilon naught r squared, and then minus 1 x hat plus 1 y hat. Alright, so now our E total is just the sum of these two, which is 3.0. Maybe I'll make a new line so I don't run out of space and don't have to squish too much. So it's going to be 3.0 nanocoulombs over root 2 8 pi epsilon naught r squared minus 1 x hat minus 1 y hat, so that was 1. And we're going to sum with 3.0 nanocoulombs over root 2 8 pi epsilon naught r squared minus 1 x hat plus 1 y hat. Okay, so that's 2. We can pull out this prefactor because it's all the same. Leaving us with just our vector math. So minus 1 x hat, minus 1 y hat, minus 1 x hat, plus 1 y hat. And so the minus 1 y hat and the plus 1 y hat are going to cancel. And then the minus 1s are going to double up. And then this is going to give us our final answer, which is minus 2 times 3.0 nanocoulombs over root 2 8 pi epsilon naught r squared x hat. So we could do a couple things with the numbers, but I think since we already are going to leave r and epsilon naught, it doesn't really matter. So I'd say this is our final answer. But again, we could make this into a 6, and we could work the numbers through, but in the end, we can use this to solve for our electric field, and we can see that it's in the negative x direction. So it's it asks what is the direction. So that's the magnitude. I guess I should finish the question. So the magnitude of the electric field is the square root of the x component squared plus the y component squared. There's only an x component, so it's the square root of minus 2 times 3 over root 2, 8 pi epsilon naught r squared. So the square root of something squared will, of course, give you the same thing back, but when you square it, it's going to get rid of the negative sign. So that's really all that matters. So the magnitude of it is going to be 2 . Okay, so it's unsigned. The magnitude doesn't have the sign. So that's the magnitude of our electric field. And the direction is in minus x. So it's towards the left or in the minus x direction. Okay, so now looking through the solutions here. Okay, so k q over r squared. So k is the same as 1 over 4 pi epsilon naught, depending on whether you want to use which constant you want to use, but they're equal, so it doesn't matter. It chose to use 45-degree angles rather than the 1 over root 2. Again, that doesn't really matter. And they pulled all the numbers together, but I presume it must come out to be the same. And so the magnitude is of 1 over r squared, and the direction is to minus x, or towards the left. So barring any calculator errors, I would say the solution is correct.